Hey guys, welcome to the section 1 recap video. So in this video we're going to be talking all about CSPs, and we're going to go over all of these concepts that you covered in lecture as recap. Alright, so let's get started with the formulation. So CSPs are going to be kind of a special category of search problem which have a set of variables. So we can call these x1, x2, x3, a set of values. So these values are going to be the values that each of these variables can take on, and then a set of constraints. And the constraints can exist in the form of unary constraints or binary constraints. A unary constraint is a constraint that only affects one variable. These are going to be just restricting the domain of a single variable. And then binary constraints are constraints that exist between two variables. So they're going to look something like this. So notice here that I've listed binary constraints as just the inequality constraint. So basically two variables can't be equal. And this is a kind of a very simple example, but in general, binary constraints can be anything. They don't have to be inequality constraints. And then kind of the goal that we're looking for is a state where all the variables are assigned to some value and none of the constraints are violated. Okay, so let's talk about how to solve these CSPs. So for that, we're going to be using this algorithm called Backtracking Search. And Backtracking Search is going to be basically a modified version of depth-first search with a couple of different changes to optimize for CSPs. So let's just walk through this search, and then I'll call attention to some of the changes as we go through. So for Backtracking Search, initially we're going to start with this empty assignment of variables. And then in each stage of this recursive backtracking method, we're going to pick one variable to assign. Now, this is kind of the first way where backtracking search is going to be different from our standard search algorithms. So the variable that we're going to assign for each stage of backtracking, we can fix that. And the reason that we can fix it is because for CSPs, it kind of doesn't really matter what order the variables are assigned in, right? As long as we have a complete assignment at the end, we don't really care if variable x1 was assigned before x5 or whatever. Okay, so by fixing our variable assignment order, there are a lot of states in the search space that we don't really have to consider. So that's kind of the first optimization that we have with backtracking search. But let's continue looking at the algorithm. So we select a variable from our fixed variable ordering. We look at all the values in the domain of that variable, and if that value can be assigned without violating any constraints, then we'll add that assignment to our set of assignments, and then we'll continue to the next variable to be assigned. Okay? And then if at any point we get a failure, what we're going to do is we're going to backtrack and remove that value from the assignment. Okay, so after we remove it, we will kind of go back to our other list of values and we'll move on to the next value to assign. All right? And then at the end here, if we don't find any values that can be assigned to our variable, we're going to go ahead and return failure. Okay, so this is another difference between backtracking search and depth-first search. So here in backtracking search, we're allowed to return failure before we reach the very bottom of our search tree, right? So why are we allowed to do that for backtracking search but not normal depth-first search? So the reason is kind of because for a standard search problem, we don't really know that we failed until we kind of get to the end and there's nothing else to explore down that branch, right? But for CSPs, that's not the case, right? Because for CSPs, if at any point in our search tree a constraint is violated, we know that there's never going to be a solution further down that branch, just because any node further down that branch will still have the same violated constraint, right? So for this reason, we can kind of return failure early if at any point there's a variable that we can't assign. Alright, great. So that's backtracking search. Like I said before, it's basically going to be depth-first search with some ordering of variables and an incremental failure test. So that's just the basic backtracking search. From there, we can kind of build on it and make a couple of optimizations. So the first of these optimizations is going to be filtering, and the goal of filtering is to discover failure before it actually happens. So if you kind of look back to the algorithm, the way that we discover failure is at any point where there are no values to assign to a variable. But sometimes we can do better than that. And if we discover failure earlier, then that means less backtracking, which means fewer search nodes that we have to expand. And then the second optimization that we consider is ordering. So ordering tells us how to pick variables and values that are more likely to give us a solution or more likely to decrease the amount of backtracking we do. Okay, so let's talk about filtering. So before we kind of get into all of the nitty-gritties of filtering, first we should talk about what it means for an arc to be consistent. Right, because the consistency of an arc is going to be the building block for the two filtering algorithms we're going to talk about later. Okay, so let's look at that first. So we'll say that an arc from variable x to variable y is consistent if for every value in the domain of x, there is a value that can be assigned in the domain of y without violating a constraint. And here below I have the pseudocode listed for checking the consistency of a single arc. Right. So these two variables, xi and xj, are going to be the two variables in our arc. So xi is going to be the tail of the arc, and xj is going to be the head of the arc. So in other words, xi maps to this x in our definition, and xj maps to this y in our definition. Okay. So to check the consistency of this arc, we will loop over all values in the domain of x sub I, and then for each of those values x, if there's no value y that can be assigned to x sub j in order to satisfy the constraint between those two variables, then we will delete x from x sub i's domain. And when this is done, basically all the values that are going to be left in the domain of x sub I are going to be safe to assign, in the sense that for any of those that we assign, we're guaranteed that we'd be able to assign something to x sub j. Excellent. So now that we've learned about consistency of a single arc, we can move on to talk about forward checking. So forward checking is the first simpler of our filtering algorithms, and it says the following. Right? So it says that after assigning some variable, we will enforce arc consistency of only the arcs that point to the variable that we just assigned. So if we look at this example that was in the lecture slides, here we've just assigned the variable WA. All right, so now if we wanted to do forward checking, we would have to check all the arcs that point to WA. So all of the variables that share a constraint with WA. And those arcs are going to be the arc from NT to WA and the arc from SA to WA, right? Because those are the ones that are adjacent on the map. Now, if we just were to walk through our consistency algorithm from the last slide, we can first look at the arc from NT to WA. So we'll basically loop through all the values in the domain of NT. So let's just start from red. So we'll say if we assign red to NT, does there exist a value in the domain of WA that we can assign without violating any constraints? And there is not, because if we assign red to NT, that means we can assign red to WA, and red is the only value in the domain of WA. So that means that we should delete red from NT's domain, okay? And the same goes for SA. So after enforcing consistency of both of these arcs, we should be left with the following, right? So NT has red removed and SA has red removed, and now these two arcs are consistent. All right, so that's forward checking. The next filtering algorithm you guys learned about is arc consistency, which is the more complex of the two. So here I have the pseudocode for arc consistency. And basically what arc consistency says is after you assign some variable, rather than only checking arcs that point to that variable, we are going to instead check all of the arcs of the CSP. Okay? And the way that we do that is by keeping track of this queue, which contains all the arcs that we still need to check. So that's initially going to be all arcs. And then while this queue isn't empty, we're going to remove an arc from the front of the queue. We're going to make sure that arc is consistent. And in the case that we removed some values from the domain of xi, the tail of the arc, we're going to have to add all arcs that then point to xi back onto the queue. Because if we remove some values from the domain of xi, then some of those arcs that point to xi might now be inconsistent, and we have to make sure that we check that. All right, great. So let's talk more about arc consistency. Again, here, instead of only enforcing arcs that point to the current assignment, instead we're going to be enforcing consistency on all arcs. and then if some variable x loses a value, then all x pointing to x must be rechecked. Okay, so it's important to note that neither of these filtering algorithms will completely prevent backtracking. They'll only kind of make it so that we can detect our failure earlier and we can backtrack earlier on the tree rather than later. So moving on, now we can talk about ordering, which is another optimization to our backtracking search. And ordering is going to determine which variable or which value we pick next. Okay, so let's talk about how we want to select our variables first. So for variables, the way that we want to pick is we want to select the variable with the fewest values left in its domain. And the intuition here is that we want to be able to fail fast, right? So we're eventually going to have to assign all of the variables. We might as well fail earlier on in the tree rather than later on, because if we backtrack earlier, it's going to be way cheaper than if we backtrack deeper in the tree. So we want to pick the variables that fail earlier. But when it comes to assigning values, or choosing which value to assign next, it's kind of going to be the opposite, right? Whereas in variable ordering, we wanted to pick the variable with the fewest values left in its domain. Here in value ordering, we're going to want to select the value that constrains the other variables the least. So it's kind of the opposite of wanting to fail fast. And the reasoning here is we have to assign all variables eventually, but we don't have to try all values. So rather than picking a value that might fail very quickly, that we might as well have not tried at all, we instead want to pick the value that has the highest chance of succeeding. Because if we get lucky with a value and it succeeds, then all of the values that we didn't check, that's just more work that we didn't have to do. Alright, moving on. So let's look at tree-structured CSPs now. So a tree-structured CSP is a special version of the CSP where the constraint graph is, well, it's tree-structured, right? And these CSPs can be solved in d squared time, which is way better than the exponential time that we're used to for search problems like this. Okay, so the basic algorithm is here. So first we want to linearize our tree. Then starting from the tail of the tree, we're going to enforce arc consistency going backwards. So that is, we're going to enforce arc consistency from the tail to the head. And then we can assign values from the head of our tree to the tail. So we're going to do arc consistency going backwards, and then we're going to assign values going forwards. And if we do this, we're guaranteed that we will never have to backtrack. And the reason that is because after we do arc consistency going backwards, all the arcs in the tree are going to be consistent, right? And that means that when we're assigning going forwards, for any value that we want to assign in the tail, there will exist a value in the head of the arc that can be assigned without violating any constraints. Okay, so we'll never be in the case where we've assigned a value in the tail and there's no values that can be assigned in the head of the arc, which means going forward, everything will just be smooth. Okay, so now that we know how to solve these tree-structured CSPs, it would be nice if we could change our other CSPs into tree-structured CSPs so we could solve them more easily. That's where Cutset Conditioning comes in. So first, let's define a cutset. A cutset is going to be a set of variables where if you remove those variables from the CSP, the remainder of the CSP becomes a tree-structured graph that we can solve easily. Okay, so now you can kind of see why finding these cutsets are useful. Basically, it's because if you find a small cutset of your graph, what you can do is instantiate that cutset with some set of values, and then you can remove it from the graph and then solve the rest of your graph as a tree-structured graph given the constraints from your cutset. And that's exactly what the algorithm is, right? So you're going to go over all of these cutset instantiations. You're going to instantiate the cutset to some instantiation, and then you're going to solve the rest of the graph using the tree-structured algorithm with the constraints given from the cutset. And then if you find success, then you can just return your solution, and otherwise just move on to the next instantiation of the cutset. Alrighty, so we are almost done. There's just a couple more topics to cover. So let's go ahead and move on to the next one, which is going to be min conflicts. Alright, So min conflicts is a type of iterative improvement algorithm which goes like this. Initially, we're going to start with a full instantiation of variables. That means every variable is going to be assigned some value, even if some of the constraints aren't satisfied. And then while the problem isn't solved, so while some constraints aren't satisfied, we're going to randomly select a conflicted variable, and then we're going to reassign that variable to a value in its domain that's least conflicted. And of course, keeping in mind that this could mean that the value for v doesn't actually change. For example, in the case where v is already assigned to its value that's least conflicted. Okay, min conflicts is going to be a form of hill climbing algorithm. And what that means is basically you have some metric that you're trying to optimize. And to do that, what you're doing is trying to improve the metric little by little with every time step. And so for the min conflicts algorithm, the metric that we're trying to improve with each time step is going to be the number of conflicted variables. Okay? Right, so it's important to note also that as hill climbing, this algorithm isn't guaranteed to find a solution. And we're not going to kind of go into all the details here, but if you just take a look at the lecture slides, it should be very simple to see. Okay, so moving on to the last topic that I wanted to cover in this recap video, simulated annealing. So here I've included the pseudocode for you guys, although I don't think that the pseudocode is the most important thing that you should know about simulated annealing. What's more important is that you have kind of a high-level understanding of what the algorithm is. So simulated annealing is another kind of randomized algorithm like iterative improvement that we covered in the last slide, except instead of always climbing up the hill, with some probability that is a function of your time, you will take a suboptimal action, okay? And this is so you can avoid being trapped at a local optimum while never reaching the global optimum. All right. So basically, the idea behind taking a suboptimal action with some probability that goes to zero as your time increases is you want enough entropy in the beginning that you can escape the local optimums, but the longer your time goes, the more confident you are that you're at the global optimum. So you're going to decrease the probability that you take a random action. And there are error bounds for this. So for simulated annealing, we're guaranteed that if your probability of taking a random action decreases slow enough and you run this for all of time, so for infinite time, you're guaranteed that you will find the global optimum. Alright, so that's all I wanted to cover in this week's lecture. So good luck on your homework and see you guys next week.